This whole thing is about trust. And specifically, it's about saying, I want to be able to trust the results of the ledger, even if I don't trust any one computer, any one party, or any small group of computers or parties. That's what it all comes down to. You really want to split it out and decentralize it so that you don't have to trust any one person or any small group of people or any one government. You want it to be decentralized so that you can trust what comes out of it.
The Prime Minister has announced the most drastic limits to our lives.
Stay at home and stay at least 2 meters away from people.
The NHS will not be able to cope to save lives.
Social distancing has become the new norm. Cafes and shops are vacant.
We've obviously shut down about half the U.S. economy.
Not only are stocks going down, gold is going down, credit's going down.
At this point, it's clear that we're going to have a recession that's more severe than the global financial crisis.
We are looking at other available options.
More and more people are buying and holding Bitcoin.
Bitcoin. Let's take a look at Bitcoin.
Some call this digital gold.
Everybody should probably have 1% of their assets in Bitcoin.
Dear crypto community and blockchain buddies across the globe, welcome back to Kryptonites, the No BS blockchain channel built with the community and for the community. And today we have another mind-blowing guest, someone who co-founded Hedera Hashgraph, who's the creator of the Hashgraph network, a data scientist, a technologist, a cryptographer, the one and only Professor Lehman Baird. But on top of this, we're going to cover some very important topics, such as the current blockchains, different DLT systems, the different consensus algorithms, which ones that work, which ones that don't, the fastest throughput, next generation blockchains, and many more interesting topics. So don't forget to stay until the very end. And also a huge shout out to Emile from the Capital for always sourcing awesome themes, topics, and questions. We love you. Don't forget to check out their website. So without further ado, Professor Lehman Baird, it's a pleasure to have you today.
Oh, thanks. It's great to be here.
All right, so to kick off, I'd love to ask you a fun question related to the evolution of cryptography. Obviously, we have old cryptography, modern day cryptography, such as the one used in movies, to try to decrypt the message of the opposing camp, et cetera, et cetera. So if you don't mind just educating us on that, that would be great.
Oh, yeah. So cryptography actually goes back thousands of years. The ancient Greeks were using it. You have the Caesar cipher, which is really trivial. Just take all your words and each letter and make it be 3 letters later in the alphabet. Or maybe not 3, maybe a different number. Very simple. And they would have, or a rod, you wrap a piece of cloth around a rod and write your letters on it, and now it has scrambled the order of your letters. And you could even combine the two. All these things go way, way back. In fact, we even think that some of the earliest writing was intended to be only this small class of people know how to read and write, and so it itself was like a cipher or a code. So that goes way back. But only more recently have we been able to get really good cryptography. And so in the 20th century, we started having stuff that would actually be secure for a long time. And then in the 21st century, we even have more cool stuff.
That's really cool. And so in modern day cryptography, like what specifically attracted you and what made you really passionate about trying to get involved in this space?
So I'm a computer scientist. I love algorithms. I've played with computers since I was a kid. Just really fun doing the math stuff for it. Cryptography is part of that. And, I taught a crypto course and taught AI. I did a lot of stuff with artificial intelligence. I like all different parts of computer science. But cryptography is fascinating. The math of it is beautiful and it's kind of fun and it's always exciting. So cryptography is cool. But other things are cool too that seem completely unrelated. Like, how could you get computers to agree on something? And yet it turns out those two start to merge. You can start with cryptocurrencies And you can start with Byzantine agreement, and then they all kind of come together. You can end up with a single thing that does both, which is kind of fun.
That is so cool. I can feel your enthusiasm from where I am right now, despite the cameras. So Professor, we'll definitely want to ask you about consensus algorithms and how these nodes agree with each other. But before that, I would love to ask you in terms of Bitcoin specifically, because as you know, DigiCash, B-Money, there were several attempts to create this sort of cryptographic or electronic cash. Why do you believe Bitcoin has been so successful so far and prevailed over the previous attempts?
It's interesting. So Bitcoin was actually very different from the digital cash that had been proposed for decades prior to it. So the idea of using digital money in some way was actually a thing in the crypto community, cryptography community, but there it was all about anonymity, not about trust. So you could say, well, I'll spend at a store and I'll have my money at a bank, and the bank can't tell who I am and the store can't tell who I am. But if they collude, then they could find out who I am. But we'll just assume they don't do that. We trust them. The big thing with Bitcoin was that, well, you didn't have that strong anonymity. You have to do mixers and things to get anonymity. It wasn't really about the anonymity. It was about not having to trust any one person or any two people. In the traditional digital cash, you'd have to trust the bank or the store to not collude with the other. But here, you could have a lot of people, and as long as they're mostly honest, you're fine. There's bad things that happen if a bad guy has all the hashing power. But, assuming that things are spread out, then assuming you can trust most of them not to combine into one bad guy with all the hashing power, then you're good. And you're actually, you have something you can trust. And so one innovation of Bitcoin was to do something simple that would allow you to have this distributed trust thing. And then if you're interested in anonymity, you do that as a layer on top of it. It's not a big deal. And cryptography had not been really thinking about that a whole lot. There was another community for fault-tolerant computing and databases. And they were worried about this trust problem, and they talked about Byzantine stuff. But that's yet another world. We have 3 different worlds here that have basically no contact at all in these early days. And I think Bitcoin got traction because that's what people really wanted at that point. And it took off, and then a lot of other systems have taken off, and some of the more modern systems have started to combine some of these different ideas. So you see systems that care about anonymity, and they're combining zero-knowledge proofs and other things in there. And you have systems that care about the trust, in a stronger mathematical sense, and so they bring in the Byzantine stuff. And so we're starting to see things combine, and it's exciting to watch it evolve over time.
It really is extremely exciting. And you just touch upon some really important points right there. So we're moving to the consensus algorithms and obviously how the computer or the nodes agree, as you mentioned in previous videos, which, by the way, guys, if you haven't seen Professor Lehman-Beard's videos in the past, check them out on YouTube. There's some really good content out there. But I'd love to ask you, Professor, obviously we have proof of work, proof of stake as kind of the more popular consensus algorithms. And I know that you guys are more specifically focusing on Byzantine fault tolerance, as you were just talking about. But before jumping into those specifics, in terms of Bitcoin itself, does it make sense that it stays on proof of work? And also, as you know, recently with Ethereum is planning on leaving proof of work for proof of stake. Do all these decisions make sense to you, and it just depends on the different use case?
So it is good to switch from proof of work to a more modern system. There are some advantages to that. You don't want the consolidation due to everybody living where the electricity is cheap. I mean, there's various reasons why you might want to do that, not require all the people to buy a supercomputer to do it. So there are reasons to switch, but it's really hard to switch. Ethereum's going to switch, I assume, but it's turned out to be kind of hard. It's just, you have everybody's using the old system. It's just hard to switch to a new system. A lot of the newer ledgers are coming along and they're Byzantine from the beginning, and they're fast from the beginning. So, will we see Bitcoin switch? Maybe not. It might just continue on what it is right now, just because it's difficult. And in a real sense, when you switch, really what you're doing is you're standing up a whole new system that's just completely unrelated, and then you're copying over the state from the old one, and you're telling everyone, just please ignore the old one now and let's go with the new one. But people could always rebel and continue the old one, and now what you've really done is forked, which isn't so nice. So that's another problem. It's hard to move forward if you don't have strong governance, that you could just move forward and other people would not move forward, and now you've split yet again. So it's a hard situation.
It's a very hard situation. And as you said, it really switching would make sense, for different generations and and how things evolved. And speaking of which, I would love to hear from you specifically about Hedera Hashgraph. Obviously, we have proof of work, proof of stake. And at Hedera Hashgraph, you guys have created a different system, the Hashgraph network. And before talking about specifically about your type of consensus algorithm, could you just explain to Hashgraph network in layman terms? So if my grandma Susie was in the room, how would she be able to understand that in the most simple way?
Oh yeah. So the Hashgraph algorithm is just a bunch of computers that are talking to each other and they want to come to an agreement. When you give them some transaction to do, some work to do, they need to come to an agreement on what order these transactions are in. Because if I tried to spend my money at two different stores, I've just spent it twice. Well, one of them should work and one of them shouldn't. So we have to know which store was first. And they get the money and then the store that was second doesn't. We have to know the order. Also, we want to put timestamps on it. We want to say, when did you really do this transaction? When did it happen? And all the computers need to agree on it. And the hard part is we want to do it even if a bunch of them are bad guys. And they're going to lie, and they're going to be malicious, and they're going to slow things down. And we have to assume the bad guys can attack the internet also, that they can slow down computers. So we want a very high bar here. I want to work even when almost a third of our computers are evil and the internet is evil. I still want it to work. Okay, so how can we do that? Well, first of all, if you hand me a transaction and I'm part of this network, I need to tell everybody else your transaction. Okay, the easiest, stupidest way to do it is I just tell someone at random. And then both of us tell someone else at random. And then someone else, each of them, now there's 4 of us. Each of us picks someone at random and tells them. Now there's 8 of us. And it just explodes exponentially. That's called a gossip protocol. It's brain dead simple, and it's about the best thing that's ever been discovered for how to get a message out fast and resiliently. How fast do rumors spread in the office or in a school? That's how fast this will spread. And how hard is it to stop a rumor from spreading? You just can't. You can't shut down one computer and stop it from spreading. So everybody uses gossip. There's gossip being used in Bitcoin and in Ethereum and in Hedera. Everybody uses gossip because it is basically the fastest, most resilient way we know to get information out. And it's just brain dead simple. There's nothing complicated. I just pick someone at random and tell them.
That's such a beautiful way to explain it. And it's so easy to understand. I love that gossip analogy. It just makes a lot of sense. You can't really stop that, can you?
You can't stop it. So for most systems, that's just the first step. And then we have to do a whole bunch of talking and complicated stuff to figure out the order. Because when you gossip, everybody gets stuff in a different order. But what if we're sending these messages around, but whenever I talk with you and I give you the messages you don't know about and you give me the ones I don't know about, that's how gossip works. What if I then created a message and in it, I just made a little note saying, here's the last one I created, and here's the last one I received from somebody else. Just 2 things. I'm just going to put a little note, a little summary of the last 2 messages, the last one I created and the last one that I received from someone else. What I'll do is I'll take those messages and I'll crunch them down to just a few bits. That's called a hash. I'll do a cryptographic hash. So I just take the hash of my last message, the hash of the last one I received, and I put them inside my message. And that's all I do. All we do is gossip with these 2 hashes inside of each message. That's it. And then to do all the complicated stuff, to try to figure out an agreement on the order and make sure it works when only some of us are malicious and some of us are good and all that complicated stuff, we don't talk to each other at all. We're done talking. Because here's the trick. If you have a whole bunch of messages, but each message you know what the previous one from that person was, well, you know the whole order of how that person sent out their messages. And if for each of those you know the last message they heard from someone else, now you have an interconnection between your order of messages and that person's order of messages. And all these interconnections form this graph, this trellis, interwoven picture of how we have talked. So you not only know all the messages, you know a complete history of how the information flowed through the network. When you hear a juicy rumor through the rumor mill, you never know who it came from originally or whose hands it passed through to get you. But in a hash graph, in this system, you know exactly how it spread. You can see the spread in your memory without talking to anyone. And this is so powerful that you can now take 30-year-old algorithms for coming to an agreement that have all these math proofs, and you can just do them in your head. These algorithms require lots of talking back and forth about voting. I just do it in my head. You don't need to vote. I know how you would have voted, and so I'll just pretend you voted that way. You don't have to tell me your vote. And you're done. And so you just do it all in your head. It's super fast. This is about as fast as the internet would allow, because gossip is the fastest way to get the information out. You have to get the information out, and then you do zero more talking beyond that, and you're done. So that's the Hashgraph way.
That's really cool. So is that the key to speed and scalability? It's the fact that you hash this information and it takes very little space in terms of storage, which allows the scalability of the chain and the speed. Is that the key point here?
That's it. That's the key point. The key point is that if you just add 2 hashes to every message, then you don't have to do anything else, because you kind of get this whole rich history for free. It just comes along for free. And so you don't have to do any other communication. The only communication you do is the gossip with these extra 2 hashes per message, and a message can be a whole bunch of transactions. So it's a very tiny overhead. And that's it.
That's fascinating. So in terms of transactions per second, throughput, and speed, how much do we really need in order to create this global ecosystem? Because as we know, with Visa, we have anywhere between 24,000 transactions per second, all the way up to, as they claim, 65,000 transactions per second. So how much do we really need, Professor?
So, the more speed, the better. But even running at 10,000 is enough to do far more than is being done on all ledgers right now. You can do a lot. So yes, you can then go to 24 million, or maybe it's 75 million. You keep hearing different numbers about what Visa needs, but you can do that. You can get all of Visa. You can go to a stock market and do that, which is interesting. A stock market is also interesting because you need fairness. You need to make sure that no one computer has too much influence on what that order is. So for stuff like a cryptocurrency, you don't care about fairness. What you care about is that we all agree on the order, but we don't care what the order is. We can have a leader make up the order. Just appoint a king to decide what the order is, and we'll all do what the king says. That's fine. But for a stock market, that doesn't work so well, because the king could decide that my order gets put in ahead of yours, even though really you submitted yours first. And maybe I slip a few extra dollars and bribe the king to do that. You don't want a leader. You want it to be fair. And so you have fairness with the Hashgraph algorithm. There's never a leader. That's why it's so resilient. You shut down one computer, we don't care, because there is no leader. It doesn't matter what computer you shut down. We don't even take turns being leaders. But it also gives you fairness. And so for a stock market, that's really important too.
That makes a lot of sense. So far we talked about different types of consensus algorithms, such as proof of work, proof of stake, delegated proof of stake. But we know that the Hashgraph network uses a different type of consensus algorithm, which is called the asynchronous Byzantine fault tolerance consensus algorithm. Do you mind telling us a little bit more about this?
So there's a lot of algorithms out there. Proof of work is basically an algorithm. Proof of stake is like a whole collection of different completely unrelated algorithms. So delegated proof of stake says we do have a leader. We have a king. We just take turns being king. And if you do a DDoS attack and you shut down the king, the whole network shuts down. And you'd say, well, that's okay. A few seconds later, we'll switch to a new king. Yeah, but then the attacker can switch to shutting him down. And so a leader-based system where you take turns being leader can be vulnerable to an attacker who can flood a computer with packets and shut it down, a DDoS attack, distributed denial of service. And so if you're taking turns being leader, there's a problem here. And so delegated proof of stake is an algorithm that has that problem. There are other algorithms. There's PBFT, practical Byzantine fault tolerance. You have the same problem. You have a leader. And so if you shut down the leader, then the whole network shuts down. Well, okay, we'll elect a new leader. Great. But the bad guys will now switch to attacking the new leader. And so you still have a problem. So we have real problems in a lot of these algorithms. Hashgraph doesn't have a leader, so you don't have that problem. These 30-year-old voting algorithms don't have a leader, so you don't have that problem. The problem with the 30-year-old voting algorithms is they're really, really slow. Hashgraph is super fast because all that voting and stuff happens in your head. You don't have to actually talk over the internet for it. So there's all these different kinds of algorithms. Many different algorithms use proof of stake, but it says that what proof of stake just means, how do you get to play? Permissioned means you only get to be a computer if we let you. Proof of work means you only get to be a computer contributing if your supercomputer uses lots of electricity and solves a hard math problem. Proof of stake means you get to be a computer if you have a large number of coins, cryptocurrency coins, or some other kind of stake. So that's just talking about who gets to participate and how much influence do you have. But the underlying algorithms allow us to get into this Byzantine stuff. And the Byzantine stuff you asked about says, how safe are we from attackers? That's what it's talking about. So first of all, it means you have to have finality, where there's a moment when you know for sure that your payment went through and it can never be reversed. With a proof of work system, you don't have finality. Maybe after 6 confirmations, you kind of trust it, but there have actually been cases where 6 wasn't enough, where you really needed 7. So those are very, very rare. That's very, very rare to happen, but that happens. You never really have finality. You never really know for sure. With a system with finality, one of these Byzantine systems, there's a moment where you actually know for sure. Guaranteed, mathematically guaranteed. If less than a third of us were malicious, we have the answer. We'll never change our mind. This is the right answer. But also to be Byzantine, you have to guarantee you're going to get the right answer, even if almost a third of the computers are evil. And there's different assumptions. Some are worse. Some say you have to have less than a fifth. But good algorithms will say less than a third. And you can't do better than that. There's a theorem that says you can't do better than that. A third is the magic number, the best you could do. And then if you want to really be good, you also want to be resilient to DDoS attacks, like I said, and other attacks on the internet, a firewall that lets some packets through and not others, and delays some and not others. And for that, you need to be asynchronous Byzantine fault tolerant. So asynchronous Byzantine fault tolerant, ABFT, is when you are secure even when attackers can do DDoS attacks and there are malicious firewalls and you have other attacks on the internet itself. That's what we're talking about.
It's so well explained. Thank you so much for sharing that, Professor. So obviously we covered 4 different types of consensus algorithms. There is also, as we know, the directed acyclic graph that I believe IOTA is using at the moment. Do you have any comments or thoughts on that specific system?
Okay, so here's yet another thing. That DAG isn't an algorithm. It's a whole class of algorithms that are completely unrelated too. So that's just a data structure inside your program. If you have a data structure that you could draw as a picture of circles connected by lines, then it's called a graph. And since we usually don't allow, we put arrows on them, so it's a directed graph, and we don't allow cycles of the arrows, so it's a directed acyclic graph, a DAG. DAGs are all over the place, and they're used all throughout computer science. Graphs are really cool. I like graph theory. It's really neat. I have some really cool open questions in graph theory I would love to solve someday. Somebody, let me know if you're ever interested in a really cool graph coloring problem. It's like Ramsey theory, but different. Ooh, really cool. So graphs are fun. And Hashgraph is a graph. Remember I told you, for each message, you have 2 hashes pointing down to 2 earlier messages. And so you can imagine it's a circle for your message and then 2 circles for the other 2 messages, and the hashes are like lines. You could draw it out as circles with lines. In fact, if you download our software and run it, it has one screen that shows you what's currently going on as a picture of circles and lines. It actually shows you the DAG on the screen. And so DAGs are useful in computer science, just like arrays are useful and lists are useful and heaps are useful. There's lots of data structures that are useful. But of course, you can build anything out of arrays. So whether it's a DAG doesn't mean whether it's good or bad. Anything could use a DAG. What's interesting then is, could you build an algorithm on a DAG or on an array or anything else that uses, that it actually achieves being Byzantine fault tolerant? That's a high bar. And then could you make it asynchronous Byzantine fault tolerant? That's even a higher bar. So other DAGs of which you were discussing aren't ABFT. They aren't even BFT. They're somewhere below that. So it is possible to make a bad algorithm out of a DAG, one that isn't even BFT. But it's also possible to make an ABFT algorithm out of a DAG. And so we are ABFT. So you could say we are using a DAG, that's our data structure. We are proof of stake, that's how we get influence. And then we are Hashgraph, which makes us ABFT and makes us fast. So that's what we are.
That is so cool. I don't think I've ever had such a great course on the different consensus algorithms and different data sets and structures. That was so fascinating. Thank you so much for that, Professor. Now, I'd love to ask you, obviously, Hedera Hashgraph, a lot of people talk about centralized, decentralized. It's more of a spectrum rather than, a specific point. But there's one question that a lot of people are asking among the community. They've asked us through our Twitter channel, which is very interesting, which is, do we need to start more centralized and then open up to becoming more decentralized? Or do we start by directly becoming decentralized and evolving afterwards? Many people have different thoughts and different perspectives on this. What is your general idea and your goal to become a fully decentralized, obviously, ecosystem?
Yeah, so we actually had a video released on the path to decentralization, how you go along that path. I think that what you really want is to make sure that you're trustworthy at every point along this path. So if you have a way to go from one way or the other, you talked about two different paths, whatever path, the important thing is to be trustworthy at every point. And so you want to have the ability to know that you're not going to have something malicious happen with your nodes. That's important. You also may have some concerns about forking. If you really want to be storing important information in your ledger, recording who owns what house, and then it forks, and now you have two ledgers that know who owns what house, and then they start evolving differently over time. Well, which one is the official one? You somehow have to make sure you never fork, or at least if you fork, you always know which is the real one and which one isn't the real one. And people argue about that after forks. So you want to be safe from forks. You want to be safe from bad governance. You want to be safe from collusion. These are all the things you have to look at to be safe from. And so they raise interesting questions. Interesting questions like, are the vast number of your nodes in one country, under one government? Maybe you trust, those nodes are being run by independent people who won't maliciously collude. Okay. Could they be nationalized by one government? And then the government force them to collude because it now owns all the computers? That's a concern. You want to make sure that you don't have that problem. Or you could say, well, who is governing this thing? Who's controlling how the code base evolves over time? And you could say, well, we have thousands of developers that are contributing. Yeah, but who's really leading this project? Does it come down to just a handful of developers? Almost every project. It's just human nature. You end up with, there's the 10 guys that really have the influence and that end up deciding where we're going. And we may have 10,000 contributors, but there's really the 10 guys. And they just it's self-organization. It's a fascinating mathematical thing in societies, how you self-organize. And this is a self-organizing kind of a case. But if you just sort of self-organized, are you really sure that they're independent? How independent are you sure they are? Especially if some of them are anonymous. So I think that what was really important that we wanted to get right from the beginning was that we would have very decentralized governance. And arguably, we have better decentralized governance than any other ledger because you know who our governors are. They are spread across different continents, under different governments, in different cultures. We are using giant companies that have been around for a long time that have a reputation to protect, so they wouldn't want to do something that harms their reputation. That's a strong motivation to not do something malicious. And they're in different industries. They're not going to collude. Also, it's set up in a way, and it's going to become even more so, where they can't do anything secretly. Anything they do bad and evil will come to light, and it will hurt their reputation. And they can't be nationalized by their government and forced to do something bad because they're all under different governments. You'd have to have all the governments on earth agree to nationalize and do something bad at once. And, governments never agree on anything. And so we have a very decentralized model. And, we have a lot of companies you've heard of. IBM and Google had joined us. And then this last week, did you hear about it? LG is now part of our council. Very excited about that. And so, South Korea is important and LG is important, and they're doing phones, which are really cool. I think in the future, every phone is going to have cryptocurrency in it. That's going to be the standard way. Maybe we'll finally be able to stop carrying wallets in our pocket and just have our phone as our wallet. I dream of that day. I want my driver's license there. I want my passport, and I want my money in my phone. I think we're getting close to that day. So I'm really excited. LG joining us is just really exciting. But that's the point, is that we wanted very diverse, large companies that are not going to want to hurt their reputation under different governance, so they can't be nationalized. And so we have the best decentralized governance that is out there. And we don't have one person with outsized influence. I can't control it. I don't own it. It's owned by Hedera, is owned by the council members. I think decentralization is very important, but it's always important to realize why. The reason it's important is because this whole thing is about trust. And specifically, it's about saying, I want to be able to trust the results of the ledger, even if I don't trust any one computer, any one party, or any small group of computers or parties. That's what it all comes down to. You want to avoid the case where you just have a handful of mining pools doing all your mining and maybe not even very many people doing all your mining. You want to avoid the case where it's controlled by just, these 10 programmers have ended up somehow having all the power, or you have a figurehead who has undue influence. You really want to split it out and decentralize it so that you don't have to trust any one person or any small group of people or any one government. You want it to be decentralized so that you can trust what comes out of it. And this is the future. Decentralization and being able to trust this way is the future.
It definitely is the future, and I'm sure many people would agree with you that decentralized governance is probably the most critical component in really measuring what decentralization means. I love how you just mentioned that, it's not about starting centralized or decentralized and scaling after. It's all about keeping trust throughout the entire process and making sure that the community understands what's going on. And as long as we're transparent and obviously have all the values of the blockchain, then we can keep that trust. So really well put. You just talked about some glimpses of the future, Professor, and I would love to hear from you. Obviously, you have the first gen blockchains, and then you have kind of next gen or more advanced systems like Hedera, Hashgraph, and other people who are trying to solve different problems. But where do we take it from here? As in, is there a next generation type of blockchain? And what would you like to see maybe by the end of this year, next year, or in the years to come?
Yeah. So what is the next step after having a single ledger that's really fast? Well, the next step is to be able to have multiple things. So you could talk about having multiple independent ledgers that can communicate with each other. You could talk about having one ledger that's multiple shards, which are like little ledgers that communicate with each other. You could talk about having sidechains. So I have the master ledger, and then I have little ledgers hanging off of it, and they periodically store some information in the master ledger. There's lots of different ways of starting to split up the world. And, you could say different applications have different ways of splitting it up. What we have realized, and I think others are now starting to realize this too, is that a really critical way of doing it, a really important way of doing it, isn't any of the three I just mentioned. It's application networks. And here the idea is you have lots of little ledgers. The little ledger does the calculations, the processing, keeps the data. It knows, if it's a cryptocurrency, it knows your balance and processes the transfers. If it's a stock market, it takes the asks and bids and figures out who wins. If it's file storage, it stores the files. The little ledger is doing all the processing and storage. The big ledger is providing the trust. All the transactions flow through the big ledger and go back to the little one. So you have the main net, and then you have these app nets, application networks. And so the application network is feeding all of its transactions through the mainnet. The mainnet puts them in order. The mainnet puts timestamps on it. The mainnet can give you cryptographic proofs that this is truly what the consensus of the mainnet was. All of your trust comes down to trusting that no more than a third of the mainnet nodes are compromised. You're trusting the mainnet nodes and its governance and its nodes and its processing. And then the appnet can be a bunch of people you don't trust at all. If you're running one of the nodes, you don't have to trust anybody else. Or if you're not running one of the nodes, you just have to hope that at least one node is honest. And you can even get them to pass along proofs from the mainnet, and you can check them. You can have auditors auditing them. And so, you can, as long as 1% of them is honest, you're fine. You can set up that kind of thing on your appnet. So very low bar. You could just use computers running in the cloud, and it doesn't really matter who runs them. You run one yourself. The appnet doesn't matter. You don't have to have trust in the people running the appnet. You inherit the trust from the mainnet. I think this is a big deal. And I was just reading this morning that other people are starting to also think that this is the right way to go. So I think that's a big part of the future. But also the other stuff is important. I think sidechains are useful. Side ledgers are useful. I think that sharding is useful. Just a single ledger that's really fast is useful. All those things are useful. But I'm excited about the first step along that path, I think, is going to be appnets. And we rolled out the Hedera consensus service earlier this year to do appnets. And I was kind of blown away by the response. So we did it because we thought people wanted appnets. But it turns out people really wanted appnets. In fact, we found that people were actually using cryptocurrency transactions not because they wanted to transfer cryptocurrency, but just because they wanted to put some information into the memo field that would be an immutable record and would have been put in order and would have gotten timestamps. In fact, they were actually using our mainnet as if they were an appnet, using a consensus service even before we built the consensus service. And so a lot of people have now moved from the mainnet to using the consensus service on appnets. It's just a natural thing. And we talked about privacy before. I said, One way of getting privacy is, you do a layer on top. And one way of doing it is zero knowledge proof stuff that gives you privacy. It turns out that's really slow. Another way of doing it is set up your own AppNet. You have total privacy in your AppNet, and it's totally fast. You're just using ordinary encryption, nothing fancy, no zero knowledge proofs or anything. And it's all flowing through the mainnet. The mainnet puts them in order and puts timestamps, but has no idea what it is they just put in order and put the timestamps on because it's encrypted. So you get total security. I think this is a big deal. And we've just rolled that out, and we're seeing amazing interest in this. Large fraction of the people we're talking to that are building on us are interested in doing HCS, Hedera Consensus Service. Then even more in the future, we'll see other things. Interoperability between networks using atomic swaps. Sharding we'll do in the future. But honestly, until we have a lot more traffic than we have now, we don't need sharding. We're fast enough. And so we won't worry about that now. But I do think that what we're going to see in the future for the world as a whole is we're going to see the world moving to more and more things moving to ledgers. Even databases, traditional databases, will eventually move to ledgers. Why not? Gives you more trust. And we'll see currencies, CBDCs, central bank digital currencies, that sort of thing happening. I think that we're going to see identity playing a bigger role, where ledgers are keeping track of who you are, actually giving you control of keeping track of who you are, but allowing you to easily prove to people who you are. There's a lot of the world that can be changed by strong identity, strong cryptocurrencies, strong digital cash, strong ways of building up privacy and having agreement and publishing things, file systems being integrated into these, IPFS kinds of things being integrated into these. You're going to see a lot of these things in the future. And Hedera plans to go right along those paths. All the paths I just said.
Look forward to seeing you guys actually advance those paths. And I think Charles Hoskinson from IOHK Cardano would agree with you, saying that, the third gen was the interoperability, cross-chain transactions, and you talked about sharding and all the things that we need to this point. But what if some people solve the problem without having to rely on sharding? That would be really interesting to see that feature. And I would love to ask you about the HBAR token. So if people want to get involved and become a part of the consensus nodes, etc., do you mind telling us a little bit about the HBAR token? Sure. We have a token. It is the HBAR. It was launched in 2018, the summer of 2018. We have a video where we push the button to launch it. It is a fixed money supply. The number of tokens will never change. It never inflates. I think that's important. We release it in the market slowly, and we have a plan. You can read our crypto economics paper. It's a very long paper on our website. Or you can look at our white paper, which is even bigger because it includes the crypto economics paper as part of it. But that's on our website. You can look at that. So we have this cryptocurrency. It is incredibly cheap to do transactions. So it's 1/100th of a cent to transfer some cryptocurrency to someone. This is a good thing. And it can pull from multiple accounts and send to multiple accounts as an atomic operation, which is useful for various things. And so that's kind of nice too. A single atomic operation does that. So there are a lot of exchanges and wallets, dozens of them. I don't remember exactly what the right number is right now. Every day we get more exchanges and wallets that support us. Our website has a list of them all and links to them all. And so you can go find exchanges that deal with it. You can find wallets that deal with it. Some of the wallets will even create an account for you. So if you don't have any accounts at all, you can create an account. Exchanges will sell you HBARs for fiat, and some of them will just take a credit card, which is kind of convenient. So you can go get a wallet that'll just create an account for you for free, and then you can go to an exchange and give them your credit card and get HBARs put into your wallet. So that's convenient. We continue to do more of that over time. At the very beginning, we wrote our own wallet, and our hope was that there would be an ecosystem of wallets and we could eventually get rid of ours. And it worked. We now have an ecosystem of wallets, and we will eventually get rid of ours. We still have ours, but we're not adding features to it. We want to get rid of it as soon as we can. But we have it, and we did release it open source. So it's useful. The source code is useful. And people can use it, but hopefully we don't need it anymore, which is nice. So we have, custodial services. There's now custodial services for HBARs. I don't know what else to say about HBARs. It's a cryptocurrency. It has all the cryptocurrency stuff. Thank you so much for that. And so if we want to follow you, Professor, what's a great way to follow your news, your writings, your reports, your blog, and of course the Hedera Hashgraph website, which we'll put the link here below. But what is the best way to stay involved in getting all the updates?
Sure. So you can go to the website, and it has links to YouTube channel. Lots of videos. This very video will eventually end up on their YouTube channel, which is kind of fun. So we have the YouTube channel of all those. We have a podcast, Gossip About Gossip. I love the name they came up with for that. We have some blogs. I think links to that are on the website too. I haven't been blogging. Paul Madsen has a really cool blog that he does. And I think some other people have blogged as well. So we have blogs. We have papers. So there's the white paper and the crypto economics paper. There is the technical report that originally defined the algorithm. You look at the peer-reviewed papers. We have that on the website. You can download a peer-reviewed paper about it and read that. It's all math stuff. I don't know if that's very interesting. Actually, for some people, that's really interesting. We have the COQ file. That one's interesting. Not only did we write an algorithm and then mathematically prove that it's the highest standard, ABFT, but then we said, well, we don't even trust that. And we have now a computerized checking of the proof, and that's COQ. And so we have the COQ files. You can download those and have your computer check the proof and see that it's right. So all that stuff's on the website. And I just appreciate any interest we get. Anyone who's interested in it, I appreciate your involvement. Oh, and don't forget, there's a hackathon going on right now. We still have a couple weeks left. You can still join the hackathon.
Oh, that's true. Yeah.
We have prizes.
All right, so there we go, guys. We had the evolution of cryptography all the way to first generation, second, third generation blockchains. What is the future like? What are the best consensus algorithms, et cetera, et cetera. So if you have your own opinions, your views, whether you agree or disagree, doesn't matter. Put them in the comment section below so that we can keep discussing and learning from each other. That's what matters the most about this channel. And don't forget to like, subscribe, and blast that bell notification so that we can keep growing the community together and make this a meaningful channel. Thank you so much, guys. And don't forget to tune in next Wednesday, premiering at a PC near you, 8 o'clock BST. One love.